So hello everyone, I'm Francesco Cirillo, and today I'm going to be presenting a new approach to software design. That sees the idea of software development transform into the idea of software production. Today I'm going to introduce two new concepts. The first one is recombining relational production, RP, and the second one is software decombination. So since I'm going to introduce new concepts, I think it's fair that you know something about my background. So I'm a software designer. I'm a methodologist specializing in software engineering. And as you've just heard, in the 80s, maybe you know me because in the 80s I created the Pomodoro technique. In the 90s I worked with Sun Microsystems as an expert on design patterns, process improvement, software development methods. In the 90s, in the late 90s, I was one of the pioneers of extreme programming in Europe. In 1999 I met Ken Beck, and then I founded the Italian community of extreme programming. In 2005, Kent asked me to be one of the reviewers of his, the second edition of his book, Extreme Programming Explained. Over time, I've lost interest in agile methods. I've always been critical about the value of Scrum and agile methods understood in their abstract sense, because there's no test. There is no test to tell you if you're going in the right direction. So it is really easy for you to deceive yourself and think that you are going in the right direction. In terms of design, I actually don't believe in the effectiveness of the solid principles when they are applied in an emergent approach to design. In 2008, I started developing and applying recombining relational production, which it is not an agile method, it is not a lean method, it is not even a method. It is a general approach to production, which means you can actually develop everything, from writing a book to develop software. Today, we're going to see how to apply this approach to software development. And let's start from the meaning. So RP, let's start with production. So with the term production, we want to create value in a more predictable, less expensive, and more sustainable way. How? Well, relational is the how. Okay, so the idea behind RP is that we can use our relational capability, the ability to look for relationship with the other, but instead than applying that with the other, we can apply that to a product, the product we are developing. And, well, we all know, we all grew up with a relational process, and so we know that relationship is really effective when it comes to growth and developing the other. There's the third point, recombining. And this is a test. Finally, we have a test. And this is a really demanding test. So I'm going to read this. Can you deliver new features just by combining already existing software modules? This can be read in two different ways. Can you deliver new features for a video game just by combining already existing software modules you developed for an accounting system? Or can you deliver new features for the user interface just by combining already existing software modules you developed for the domain? It's a demanding test, right? Good. Decombination is the second concept, and decombination is one of the relational operations undertaken in RP. It is the result of looking for relationship. And it's really effective because it enables us to find highly recombinable software modules which can produce value in various and unpredictable contexts. So the same building blocks can be used to make a video game or an accounting system or something we don't even know right now. I don't think you want to make a sandwich with a cake. I don't think you want to put a chocolate cake on a slice of pizza. I don't think you'd like a traditional lasagna filled with chocolate cake. The cake is a combinant characterized by a low degree of recombinability. 0. I don't want chocolate cake in my software inventory. I want ingredients. I want ingredients I can use in various contexts, from appetizers to pasta, soups, and I'm going to have recipes. And I want to apply those ingredients even in unpredictable contexts. You know that you can use flour and water, which are exactly the same combinants you use to make the chocolate cake, for glue. And you can make glue out of those two combinants. I want my software inventory to contain ingredients so that my inventory can become a valuable asset rather than a costly liability. Now, if you want to understand this definition of decombination, keep in mind that cake is A, and maybe flour and eggs are B and C. Okay? So, relational operation oriented to finding a combination of combinants, so flour and eggs, able to replace an already existing combinant, A, the cake, while reproducing the same behavioral utility or value. And this is a recipe, A equals B equals C. So as to reduce the number of low recombinable combinants, again, the cake, and increase the number of highly recombinable combinants. So again, flour and eggs. Thus allowing the average degree of recombinability of the combinants in the system to increase. This is our strategy. From now on, this will be our strategy. Okay, so this is what we are going to do. Firstly, I'm going to introduce the WA decision-making model. This is a model of the mind I've developed to help us make effective decisions when faced with uncertainty. RP is based on this model, and this is why this is relevant today. Then we'll see how to look for relationship with a piece of software, and how we can apply decombination to software. Okay, let's get started. First question: what is a WA? Okay, imagine there is a baby in front of you, and this is not your baby. This is a baby you don't know. The baby starts crying, and you feel the need to do something, but you don't know what to do. Okay? This is a WA. This is something that comes from inside. Okay? You can have this WA also when you develop software, right? Have you ever found yourself staring at a blinking cursor? You feel the need to do something, you didn't know what to do. This is a WA. Okay? Now, why are these WA important? Because from that moment, from that perception, stems a decision. Okay? And what kind of decision? It could be a decision to do something or a decision not to do anything. Typically, we focus on decisions. We focus on the result of our WA. And we are not aware, we don't even recognize the process that starts with this perception and ends with the decision. And instead, this process is important. Well, the point is that developing something, software or something else, doesn't involve just one big decision, right? It's a long series of teeny tiny decisions, right? And each of those decisions is relevant to the final outcome. Each of those decisions shape the behavior and the structure of the other we are developing. So, it is really important to know how we respond to these what. And if you follow the what decision-making model, there are just two different types of response. There is an inward response, which means by exerting control over the other, or an outward response, by looking for a relationship with the other. So in the first case, we apply force. This is a typical protection mechanism. And we make an effort to adapt the other in terms of what we already know. Our knowledge, our patterns, something we know. In the second case instead values trust. Okay, it's based on trust. So what we do is that we make an effort to adapt our current knowledge in terms of the other. You can see those two responses, these two types of responses as two drivers. Okay? And at every walk, you choose which driver you want to take the next step. Now, it's really interesting how these two drivers see the same things. So, for instance, uncertainty. And control sees uncertainty as a risk. And to protect us, it adapts towards known structures and patterns. And relationship, instead, sees uncertainty as an opportunity. And through dialogue, it favors uncertainty of the answer and allows the other to freely express itself. Well, you know what? Today, we're going to see how we can actually apply this driver. And I want you to understand how these drivers can be used to reach a goal. In development, we have to reach goals, right? And the goal we want to reach is weaning a baby. So we want our baby to eat solid foods. I think it's pretty easy to imagine how control would behave. Okay, so basically we prepare what we consider the best smoothie, and then we make our best to put the spoonful of smoothie in the baby's mouth. And this process can take hours. It could be really frustrating, both for the baby and for us. And you know what? Even at the end of this process, we haven't actually solved the problem, because tomorrow the problem will come again, because we are not sure that the baby likes the smoothie. Okay, let's see the second driver. Okay, so this is a real example. Lisa is Craig's mom. She prepares 3 different smoothies. She take Craig in the bathtub. She put the smoothies there, and little Craig, starts doing something with the smoothies. Put some of the first one in the mouth and grimaces, and then keep going and tries the other smoothies, and at the end, he eats one of them. And he clearly say, okay, I like carrots. We really want to analyze what happened here. And so let's see. So, because we want to do this with software. Lisa trusts little Craig. Lisa leaves little Craig free to express himself. Lisa creates a channel. Little Craig doesn't speak our language, right? And the channel is the bathtub plus the smoothies, this kind of setup. Lisa's solution takes more time, right? And requires a more complex setup. Lisa favors the uncertainty of the answer, and tomorrow Craig will help Lisa, because we know what he likes. Okay, not saying that control is not effective, okay? It depends on the context, okay? If we have a context characterized by little information, no change, control is perfect. The point is, even RP will use control, okay? But not to grow or to develop the other, okay? Growth is characterized by lots of information and change. Okay, second part, how to look for a relationship with software and how to get to software decombination. Okay, does anyone know what this is? And what kind of application can you find this code? What kind of application can this be?
The car race.
The what?
Car race?
I'm sorry, I didn't understand.
A car race, maybe.
Okay, something like a game.
Yeah.
Good,
Okay.
perfect. This is the game Pong. Okay, this is a code extracted from that game. Two paddles return the ball back and forth, right? So since we're old, okay? And this is Gabriele. Gabriele is one of my students on the RP program, and he decided to develop this Pong game to learn RP. Now, this is our screen. Do you remember what Lisa did? Little Craig doesn't speak our own language, and so she created a channel. And one way of creating channels with our software is through relational activators, those tools you see around this Pong game. Okay? And there are lots of different relational activators. There's one for the ball, one for the game, one for the board, one for the wall, one for the paddle left, one for the paddle right, etc. Why do we do this? We do this because we want to look for a relationship, and to look for a relationship we need, with important part of our software, and to do that we need channels, okay? And those are channels. Our client didn't require these things, okay? So we are violating lots of principles here, okay? But we really need them. And another point is, those activators, they work with the system when the system is alive, okay? So what can we do with an activator? Well, we can send messages, send requests, ask questions. The activator could show the properties of the particular element, okay? And the activator can actually ask, the element can ask things through the activator. So we basically can develop the behavior of those parts through those activators. Okay, when we started working with Gabriele, we didn't have many elements. We just had one ball, one paddle, the board, and two activators. The activator of the board and the one of the ball. Now we're going to see how we use these activators. So this is the activator of the ball. This will be a really simple use. This is really basic. And what we're going to do now is saying, next. This is the code, okay? And the ball goes here. And then we say next again, and this is a what? Right? We expected the ball to bounce. And again, and no, the ball goes straight. This is a big one. Okay? Okay, what I'm going to do now is to start from this what. In this board, we recorded all the what and all the processes and the final result, okay? And why this is relevant? Because those 2 points are 2 decombinations, okay? So I can actually show you those 2 decombinations, one by one. So let's get started. Okay, so Gabriele just noticed a big one. The ball touches the paddle but doesn't bounce. So this is the code, and this is the design we have. Okay, we have to explain this design a little bit. So we have a next message. The ball receives this message. Then the ball asks, is anyone colliding with me, to the board. Then the board, okay, then the board asks back, what is going to be your next position? And to answer this question, the ball goes to the trajectory, and the trajectory creates a new coordinate. Now we know that the next position will be 10-10. Now the board goes to the paddle and asks the same question, 10-10. Now the board calculates and says, yeah, you are going to overlap with something, and then the ball has to change trajectory. Okay, so it goes to the trajectory, the current trajectory says, change trajectory, this trajectory creates a new trajectory, change direction, this creates a new trajectory, and at the end, we ask the new trajectory, move me. This is the design, but apparently it doesn't work. Okay? Well, for sure, here, there's a lot of control, right? Because the board knows all the elements and coordinates them to detect a possible collision, okay? And this leads us to our second what. And the second what is from Gabriele. And Gabriele says, what if the game gets very big? What are we going to do about performance? Okay? And very big means lots of active game objects, huge game field, okay? Sometimes we have these one which are driven by fear, okay? This could be one of them. So we can actually say, oh, This is never going to happen for our little game, okay? But they instead decide, okay, we want to work with it. Okay, so we're going to write control solutions on one side and relational solution on the other side, okay? And the control solution is right in front of us. The board needs to communicate with all the objects in the game. What would relationship do? And the answer is, the board is aware of itself and of its action. This is kind of new, right? What is a board aware? What does it mean? Well, we expect the board to be able to answer to some questions about its properties and the actions the board is doing. Remember that the board is alive. The board is alive in this case, okay? And now we have two questions. What kind of messages, what kind of questions, and how we can ask questions. Actually, the second question, we already know the answer. We have activators. And so what we have to do now is to come up with a bunch of questions. Okay, so we brainstorm and we produce some questions. Which objects are on your board? If there is a ball, what would you do? You see, not only questions, sometimes requests, sometimes messages. If there is a ball, play a beep. If there is more than one object, play 2 beeps. And again, others. Which objects are on you at coordinate 10, 10? What would you do if there is more than one object at coordinate 10, 10? If there's more than one object in cell 10, 10, will you beep? This is a question. If there is more than one object on coordinate 10, 10, change their trajectory. Nothing of this has been requested by our customer, right? But if our board is able to answer this question, I would say that the board is aware. Is aware of its actions, of its structure, of its properties. Okay, so let's do this. The first thing we notice is that this question could be tricky. We have to develop the software to answer all these questions. And so we think, what kind of lines of code could actually solve this problem? And we start saying, okay, the board knows a collection of game objects, and maybe we want to check if each of those objects overlap a specific coordinate. This is really time consuming if we think of the what. So the claim is really, really big, and this kind of thing, this is not going to work. And of course, we have another problem with the next question, because what would you do if there's more than one object at coordinate 10, 10? Well, I expect the board to answer to this question, and it's pretty difficult. So we are thinking, what should we do here? And we say, oh, maybe the board is not the right object. We should ask these questions. Maybe we should ask this question to the cell. Okay, now what I'm suggesting here is not that the board knows the cells, but that we can find a particular combination of cells which will get rid of the board. So that we have something like this. And this is our first decombination. So what we want to have is a bunch of cells organized in a specific way, and this way we can generate the same behavior as the board. So if this is true, I can get rid of the board, and I can say the board is decombined. And the effect is that we eliminate a low recombinable object. The board is like a cake, and instead we have highly recombinable objects, cells. And you can ask, okay, why are those objects more recombinable? Because it is easy to see other combinations, other recipes we can make out of the same ingredient. Okay? Okay. Although there is no longer the board, we keep the board activator. And the board activator is now speaking to the cell, to those combination of cells. Okay. So now we have another why. And this why is, will the cell behave in the same way as the board? Is this really true? Is this the combination real? Okay, so the answer is ask your software. This is a relational answer. And we are going to start. This is our question. And this is the design. And the design is more complex, right? Because now we don't have the board and we have a combination of cells. And the ball has to unregister from one cell and register to the next cell. And here we have another object, more than one game object. This is a rule. And this rule checks if there's more than one object. If so, it starts another object, and this object is player B. And this was one of the questions we wanted to answer to ask the activator. It works for us. Of course, it is more complex, but it works. Okay? So we want really to be sure, and we want to try with another request. And the next request is, if there is more than one object on coordinate 10, 10, change their trajectory, right? Well, kind of easy now, right? Because we change the position, so the ball goes from cell 1110 to cell 1010, and at that very moment, we can create a class, right? Change ball direction, and this class is going to send a message to the ball, and here we have another big wow, because this is exerting control. Okay? I don't think anybody likes being told what to do, where to go, or how to do things, right? And this is exactly what we're doing to our little ball. So we don't like impositions. Remember what Lisa did, okay? What can we do to let the ball express itself? What can we do in order to let the ball help us? Okay? We don't want to apply force. So the solution can be, we can just tell the ball, okay? Tell the ball and say, you just collided with something. And we trust the ball. Uncertainty is really high now, okay? Because we don't know what the ball is going to do. And maybe we program a really good DNA for the ball, and then the ball can actually change trajectory. But at the same time, we could actually say, but the ball is going to help us. Yes, because the ball, tomorrow we can actually ask the ball to not change trajectory, but change color or disappear. And this is really easy, right? And if I have an activator of the ball, I can actually ask the activator, ball, what are you going to do when you're colliding with something? And I expect the activator to say, yeah, we're going to change color and change trajectory. Can we do that? Okay. Okay. But this is not done. We're not done because we have the second part. And the second part is the paddle. And of course, we can actually do the same thing, right? We can communicate to the paddle, okay, handle collision. And the paddle will do something. In this case, the paddle will do nothing, right? So it is not really relevant. So for us, this is okay. Okay, let's compare what we've done with what Lisa did before. So you see, we trust our software, ball, paddle, cell. We leave the ball, paddle, and cell free to express themselves. We create activators because they don't speak our language. Our solution takes time and is more complex than the other solution. We increase the uncertainty of the answer of ball, paddle, and cell, but tomorrow, the ball, the paddle, and the cell will help us change their behavior. Okay, but we feel another big decombination in the air. And the decombination is related to paddle and ball. How can I express ball and paddle in terms of a combination of combinants? Okay, well, the idea starts from this slide, actually. Okay, this slide here. You see, we have this player beep here, but this was just for the activator. But instead, we know that this player beep belongs to the paddle, right? Someone bounces the paddle, and we want beep, okay? So if we want to do this, it's really easy, right? We just apply the handler, we just apply the player beep, and we are done. So what is the difference between a ball and a paddle, right? Well, they both occupy a cell, they both have an handler, and that's it. Okay, so this is the point. Now we need to write. Because one thing I would like you to have in mind is that what I'm doing is not a decomposition. What I'm doing is a decombination. So let's see. And the decomposition is, of course, exerting control. So how decomposing works? So we isolate, we separate, and extract common behavior. And then we refactor this common behavior in the superclass, maybe, game object. Or we refactor this common behavior in some strategies. Right? We extract methods, we do these really nice things. Instead, what we are saying is that we're going to decombine. And decombining means to unite. Exactly the opposite, if you notice. We want to unite. We want to combine to bring together different behavior. We want to express the ball and the paddle in terms of a combination of combinants. And we're going to get rid of that hierarchy. Ready? So we want to do this. The point is how. And this is how. We create recipes. But this time, to create this recipe, we need an item, right? So we can express a ball as an item which stays on a cell, and it has a trajectory, and it has a handler, and it has a command configured as a change trajectory. And the paddle is an item which stays on several cells, maybe, and there's a position calculator that could be easily decombined with the trajectory because they do almost the same stuff. And it has a handler and a command which is configured as a play, a beat. Okay, so if this is true, bye-bye. We just decombine two objects, two really low recombinable objects. Okay, and this is the solution. We have items instead of ball and paddle. And now we have the next one. What about the game object? Can we get rid of it? Of course. Okay, game objects are what? We have walls, right? We have two different kinds of walls, right? Because the left and right walls, they update the score. If the ball touches those boards, the score is updated. The other boards instead, they're really nothing special. So we start. And this is a recipe for the left and the right border, right? So it's exactly the same recipe, but we have to configure those objects, those commands, a little bit different. We have to create just this update score class. So if we want to develop this, you have to focus on this now. The cost is really low, because we just have to create an extension, and that's it. And what if we have to create the top border and the bottom border? Well, they are for free. Mm-hmm. We already have all the elements. You see? We just have to combine those elements. And we have the top border and the bottom border. And what we really did, we just decombined those objects. We can eliminate these elements. And, of course, we can eliminate game object. We don't need it anymore. Okay. And this is the result. You see? We have all those cakes. We remove those cakes. And instead we want ingredients. And we have three different repositories. So the first repository is the recipes repository. So here we have all the recipes, all the combinations. The second repository is the ingredients, the combinants. In the code we will have these three repositories. Yeah? And the third repository is extensions, so configurations of combinants. Okay? Okay. So now I'd like to share an observation with you. This code is really reassuring. We know everything. We know what is going to happen, right? It's really, really clear. If you collide, you're going to change directory. This is really clear. And you know that when we have this kind of feeling, being reassured, this is driven by control. So there's control behind this code. Well, this is less reassuring, right? This is our palm game. Can you distinguish where the paddle is? It's not easy. Even if I help you, it's still not easy. But if I do this, then it's easy. Those are the recipes. And if I do this, then it's easier, right? Okay? So don't fear complexity, structural complexity. Because in RP we have two tools, recipes and activators. And those two tools handle uncertainty and structural complexity. Okay, let's get back to Gabriele. Now Gabriele he wants to make a Tetris out of the same elements. I don't want to spoil it for you, but it should be simple to understand how to create a new recipe for Tetris. But this is a magical moment for Gabriele, so I want to talk about this. This is a really important moment. Because, obviously, I was able to capture his excitement. Because he had the idea that he could actually use the same combinants, the ones we developed for Pong, to develop a workflow engine. And this is his engine. You remember? With ingredients, right? Unpredictable context, right? Now, I don't want to spoil it, but I want to show you how we could do this. So we have kind of a cursor. This is a ball, right? And the ball now registers on a cell, and this cell now is a step. And when this happens, we have this comment here, this rule here that says if more than one element are me, well then trigger number one, trigger number two. But in this case, we're going to trigger an action, and this is our paddle, and this action is going to read emails from Gmail account, and then it's going to trigger again the ball, and in this case, the ball go ahead to the next step. And the next step will be forward emails to our account. Okay, this is super good. Because you see, with the same combinants, we just got 3 different recipes. And you understand that our strategy is, we don't want to have many combinants, but we want them to be really highly, they must have a really high degree of recombinability. And we are super happy if the repositories grow and grow and grow. This is value, right? Okay, another observation I'd like to share with you. So our combinants are different from the one we could get if we followed object-oriented design or functional design principles. And this is not a matter of programming paradigm. Our combinants could actually take the shape of objects or functions. This doesn't matter. Okay? The difference stems instead from the fact that those paradigms are driven by control. All the design principles you know, traditional, agile, both if you apply them to functions or objects, are by construction driven by control. Why? Because you see the other in front of you as a bunch of lines of code, and not as a system, as a living system that can actually have a reliable behavior. Now let's see this point. What are the principles? All those principles are based on the same things. Isolate, separate, substitute. In fact, we apply separation of concern, divide and conquer. You feel it? It's an imposition over our code. We make the decisions. And control is not effective in a growth scenario. And this is the final result. The result is that at most we obtain pieces of puzzle. And the degree of recombinability equals to 0. We have a class specific, we have the bottle, we have the ball. Those classes are specific for that particular game. You can reuse those things in another game. It's worse than that. Because we actually create different puzzles to develop the user interface, the business logic, the data access layer. And each puzzle has its own specific software modules. 0. Those are cakes. We don't want cakes in our software inventory. We want highly recombinable components so that it can be used to build the UI layer, as well as the business object layer, as well as the data access layer, everything. No cakes. We want ingredients and recipes. A final observation. This chart shows the cost of change. It measures the cost of a new feature over time. Typically, this curve tends to grow over time. This is the traditional curve, but also the agile curve. Sooner or later, goes up. This is, I guess, the first time that you see this curve to decrease over time. And it should be clear why. Because over time, we produce, we develop, we create value, recombining and not developing. Recombining costs less. Sometimes costs nothing. You remember when we decombine those elements, the walls? Sometimes we just have to configure components, sometimes we just have to write a new recipe. And of course, if I have to recombine components, well, it is easier to estimate, right? I can easily estimate a recombination. And it's really difficult to estimate development, which is exploration. Well, I don't want you to get the idea that our main goal now is to find the best combinant, right? Remember, control did that. You prepared the best smoothie, and then you make your best to put the smoothie in the mouth of the baby. No. The next question will be how to decombine cells and how to decombine items. So, I think I covered this point. So, RP and software decombination turn development into production. So, I really think I covered those 2 points. And so, I think we have time for some questions. And there's also the open space. So, if I have other slides, we developed with this approach. This is from 2008. How many years? 7 years. So our system name is Henry, so we can actually use the open space to see more slides or to do other things. Question?
Thank you, Francesco.